In the last video, we talked about searching through binary search trees. Today, we're going to talk about, or in this video, we're going to talk about actually maintaining and adding items to binary search trees, which is a little bit easier than maintaining a sorted array, right? And we'll see that in a minute. So remember that a binary search tree is sort of like a sorted array in that the middle of the array has these two nodes, and on the left side of the tree are all the values that are less than the thing at the root, and all of the things on the right subtree have a value that's greater than the value at the root. And a balanced subtree provides basically the same search time as binary search on an array, except that we can add to it a little bit faster. So the basic idea here, so to maintain the binary search tree properties, when we add a new value to the tree, we need to make sure that it goes in the right location. So we want to insert it into the tree in a way that we're not going to violate any of the properties of the tree, which basically means that it always needs to go on the left or the right side depending on its value relative to each node in the tree. So we're going to use a procedure that's very similar to the search algorithm that we talked about in the last video. And the basic idea is that you follow the path down until you hit a null pointer in the direction you need to go to find that particular value. And when we hit that null pointer, we're going to just create a new node and insert it there. So here's the algorithm in sort of in pseudocode. So starting with again, we start with the root as our current node, and at each node we compare the value at the current node with that of our thing that we're inserting. If the value of the current node is bigger, then depending on whether or not the left child is null, we're either going to create a new node right there with our new value, or we're going to recursively call insert on that left subtree. Right? Similarly, if the current value is less than the insert, then we're going to recursively call in the right child or create a new right child. Right? So let's look at this for 13, which last time in the other video we saw that 13 doesn't exist in our list. And the idea is that we start at 8. Well, 8's smaller than 13, so it must be in the right child. So, 15 is bigger than 13, so it's got to be in the left child. And at 13, it must be in the right child because it's smaller. But now we've hit that null pointer, right? And we can say that if the value of our current node is less than our insert value, and the right pointer is null, which it is here, right? We've reached the end of the tree. We're going to create a new node with that value. So now the right child of 12 is 13. And again, that maintains our property that 13 is bigger than 8, less than 15, bigger than 12, right? So now this is still a proper binary search tree, right? Well, what if now we wanted to insert 14? Where should 14 go in this tree? Well, it's greater than 8, so it needs to be in the right subtree. It's smaller than 15, so it needs to be in this left subtree. It's greater than 12, so it needs to be on this right subtree. And when we get to 13, it should go on the right, but that pointer is null. So it doesn't exist, so we create a new node here. And we can see after adding this node, the tree is no longer very balanced, right? The tree is getting to a point where it's a little funky. If we're looking for, say we were looking for, 14 and a half, right? I never said these are all integers, but say we were looking for 14 and a half, now the traversal is much longer than if we were looking for 6, right? If we were looking for 6, which isn't here, 14 and a half is not here, but it takes us 1, 2, 3, 4, 5 lookups. Looking for 6 takes us 1, 2, 3 to know that it's not there. So we'll talk in some later videos on how to maintain a balanced tree, right? But for now, just inserting into a binary search tree and maintaining the binary search tree-ness, right, is done by simply using the same search algorithm that we had before, and then when you hit the null pointer, right, when you hit your first null pointer, you insert a new node. So this algorithm does assume, right, that the value is not already in the tree. So you could run a search first, and then if it's not there, then you can insert it. Right? You could build those two together, and we will probably do that in class on how to shortcut the search.